This work was, this is the primary person on the work, Rojing. She's a student of mine, and we use many of the tools developed by Johnny Gray, who's a staff scientist in my group. Okay, so let me just first start out by defining tensor networks. I think if you're familiar with quantum circuits, then this audience should be, then you will know what tensor networks are. Tensor network are very similar to quantum circuits. In fact, quantum circuits are just a subclass of tensor networks where every tensor is unitary. Now, in the case of a quantum circuit where the tensors are unitary, then there's a notion of input and output in the definition of these unitaries, these multi-leg unitaries, and that means that a quantum circuit has some implicit notion of time associated with it. But today I'm going to be talking not about unitary tensor networks or quantum circuits, but the more general type of tensor network where the tensors can have arbitrary values. And consequently, because there's no unitary constraint, there's also not really a real implicit notion of time. So given a tensor network, the basic computation is to contract it, and many different types of problems can be expressed as a contraction of a large tensor network. So, for example, okay, so this is the sort of mathematical definition of the contraction, right? So you have tensors which live at the vertices of a graph, and you have some indices that are the edges. These indices index into the tensors, and the contraction is this basically summation of all the products of the vertices summing over all the edges which index the elements of the tensor. So many problems can be expressed essentially as this type of computation. For example, quantum circuit simulation is this type of contraction, and so consequently, tensor network contraction is very relevant to many types of quantum applications. But it's not the only setting, and quantum is not the only setting in which tensor network contraction appears. There are many others. For example, when you evaluate classical partition functions, it's exactly of this form. In sort of a CS sense, if you're doing counting the solutions of satisfiability problems, model counting, it also can be expressed this way. And the application that I'm going to talk about today, multivariable integration, can also be thought of as having this structure. And in these other applications, of which there are many more, I'll point out that the non-unitary nature of the tensor is sort of natural to the problem, and that's why we are using general tensor networks, not unitary tensor networks. Okay, so when it comes to tensor network contraction, that's just some gigantic nested sum. You know, in the general sense, it's exponentially hard. If you have a lot of tensors, then in the worst case, you know, it's just an exponential number of things to add up. But you can change the order of the sum and change the cost a lot. So it can be sort of a good exponential or a bad exponential. And we can have very dramatic changes in cost depending on the contraction order. That's something which has been sort of seen a lot in the quantum context. For example, in quantum circuit simulation, as I mentioned, you contract some gigantic tensor network. This is the simulation of the supremacy circuit on Sycamore. It's just this gigantic tensor network. And you can imagine that there's many different orders in which you can do the contractions. You can rearrange the sum in many ways, and that can change the cost by a lot. For example, if you take sort of a bad order, then you get the time to do this as being 100 billion years. If you do in a reasonable order, you get something like 10,000 years. This was the original published number, the Google paper. And if you kind of choose a better order, you can reduce this much further to just a matter of days or even less. Today, however, I'm probably not going to be talking about exact tensor network contraction, but approximate tensor network contraction, because exponential is not necessarily what we're interested in. We want sort of better scalings. So it's important to note that when you have tensor network contraction, it comes with a kind of sort of very natural sense of approximation associated with it, because these are sort of linear operations, and there's a lot of approximations in linear algebra. And the easiest way to explain this approximation is just from matrix multiplication, which is a tensor contraction just of two very simple tensors, each of which has two indices. So matrix multiplication, you can multiply these two tensors together, but you can approximate the result by a low-rank decomposition where each of the tensors is now replaced by a rectangle, where the rectangular dimension here, m, is less than n. In this case, we would say in the tensor network language that we've compressed the bond being the index you're contracted over, to a smaller dimension, m. Okay, so this low rank factorization is the compression. And there are, of course, many choices of exactly how you do this. But that's roughly the idea. So imagine that you have some tensor network and it has like these double bonds between these tensors here. You can imagine replacing this double bond, which is basically a very large, high-dimensional, large value of this index into some lower rank form. So that would be the compression. And you can do this for arbitrary structures. So this would be some two-dimensional tensor network. So in contracting it to produce the result, which is a scalar at the end in this case, you would contract, you'd produce some larger tensors which have larger dimensions, and then you can compress them at some step. For example, somewhere the double bond is turned to a single bond, and that is this type of factorization occurring. Now, these types of approximations, it's hard to prove anything theoretically about them in the general tensor network setting. And so it's possible to be very pessimistic because in some worst case settings, they don't work because we know, exact tensor network contraction has to be exponential in some setting, and the approximations will not necessarily work all the time. But in reality, it's one of those things where often they work extremely well, much better than you ever expect. And just to give some examples in the physics simulation setting, the kind that we usually do, there's an example of computation of a partition function for a very complicated lattice. This is a frustrated three-dimensional lattice, a Polynomial lattice. We're computing the Ising model partition function at the critical point, so the most difficult point in the model, and compressing down to extremely small dimensions during the contraction, just dimension 8, the very small tensors, you can compute the free energy to very good error, to 1 part in 10 to the 4th. So it's very, very compressible, even though it looks like it's a very, very hard problem. And then on the right-hand side, I show a quantum case, which is a simulation of the Heisenberg, 3D Heisenberg model. And here you can just do simulations of ground state to many, many sites, 1,000 sites. And all I'm trying to say is that you can do this with very low bond dimension with very good error. Okay, so that's just to say that although there are no theoretical guarantees with approximate contraction, in practice, it can work extremely well. And that's what we're going to really be relying on. Okay, so now let's get to the actual problem we're going to study, which is multivariable function integration. So that's, just this thing here. We all know what it is. And it's sort of the grandfather or grandperson of the curse of dimensionality. Now, there are many different ways to do this, but the context in which there's this curse of dimensionality is in the context of quadrature. And then you say, well, if I put a number of quadrature points along each dimension, then the number of quadrature points is obviously scaling with the number of variables n. That's the curse of dimensionality. So people have tried to do other things to bypass this dimensionality problem. Monte Carlo is one of the examples. In Monte Carlo, it's stochastic, so the error is not sort of known immediately. And the dimensionality doesn't immediately appear, but it can essentially reappear in the fact that the error depends on this variant. And when you have very oscillatory integrands, then in fact the variance can have the dependence on dimension, and in fact even an exponential dependence on dimension. And so in fact, things are hidden in the sigma. And then then another technique, quasi-Monte Carlo, it still has this exponential dependence on n, but with some different factor, and this sort of limits these types of methods to only modest dimension. Okay, so the question is, can we invent a different integration strategy using the ideas of tensor networks? Okay, so the basic point is that quadrature is some gigantic sum. If I take a product rule, it's just some nested sum like this. And tensor networks are some nested sum. So if I can convert this into this, then I can express this as tensor network contraction, and then somehow contract to exactly approximately, and then I've done the integration. The only issue is that I have to turn the function into a tensor network. Okay, so if I just write down a function, it's not immediately obvious that it's a tensor network. So there's a few ways to proceed. One is you can try and approximate the function, for example, by fitting it perhaps at some sample points to some predetermined tensor network ansatz. And that's a reasonable strategy. But it's not what we're going to use today. I mean, it has a variety of drawbacks. One is it introduces another level of approximation. So the strategy that we're instead going to use is we're going to represent the function directly by computational circuit, an arithmetic circuit, and then we'll see that that arithmetic circuit can be directly translated to a tensor network. So this is what we're going to do today. Okay. So what's an arithmetic circuit? Hopefully people know, but functions can be composed from basic operations, addition, subtraction, multiplication, things like that. I'm not going to treat division because division is not a necessary component in arithmetic circuits. And if you look inside, your computer, it's of course doing everything in terms of these circuits, and it's using classical circuits. So in a classical circuit, the usual point is that you represent your numbers in binary. So floating points are very, very long strings of binaries. And then the logic gates are doing the arithmetic. So this is an addition gate, which takes binary inputs and has binary outputs. Now, in principle, everything here is a tensor, right? So the logic gate is a tensor where the indices are just binary indices. And so consequently, if you know this logic gate representation of your function, you actually have your function as a tensor network in principle. But in practice, this type of classical circuit is extremely large because you have lots of logic gates and you have just enormous number of tensors, so it's not very practical. And in some ways, it's very inefficient because it's not using general tensors. The values of the tensors are all 1 and 0 and extremely sparse. So one might say, okay, why don't we use fancier tensors? Let's think about quantum circuits, and you can do arithmetic with quantum circuits. And then you have a question of how you represent your numbers again. You could represent them in binary and qubits, but that's again kind of very, very inefficient. There are other possibilities. So for example, you could store the number as a phase of a unitary and then manipulate this phase. This, for example, has been studied before by Nathan and Martin Röttler. And this is, again, a tensor network because all the unitaries are obviously tensors, and the floating point numbers are stored very compactly now because they're stored as a phase. But the downside with this is that the arithmetic is very, very indirect because it's relying on sort of adjusting these nonlinear maps of angles, and they're not really directly doing addition and multiplication and so on and so forth. Well, at least they're not doing multiplication directly, and so it's a little bit complex. So there's a much simpler way to do all this arithmetic, though, if you allow yourself general tensors, and this is exactly what I'm going to show now, and it's a representation for you. So imagine that you have these your function, the univariate function, represented on a grid. Okay, so it's just a list of values, just a vector of values. So I'm just going to store these floating point numbers directly in the entries of a tensor. Okay, so this is going to be the tensor representation containing the vector values. And then to do arithmetic, I'm going to on these numbers, I'm going to have this additional binary control index here, which can be 1 or 0. And when I set it to 1, then I get the function values. And when I set it to 0, I just get back 1. Okay, so it's like a switch which turns the function from its values from values to 1. And this is obviously a compact representation of floating point numbers. The floating point numbers are just stored in the tensor. And then to do arithmetic, it's then in fact extremely simple. I just operate on this binary control index. Okay, so to do addition, I just have to have this binary logic gate, which is just got sort of 2 inputs and 1 output. It's just a 3-index tensor. All the entries are 0, except in the case where these two are 1 and 0 and 0, 1, and the output is 1. In this case, this particular entry is 1. Multiplication is similarly just done by acting on these control digits with this very simple tensor, which is all 0, except when all the indices are 1. And then this is 1. And then finally, it's convenient if you want to do nonlinear things to copy stuff. Okay, so this is not quantum circuits. We can copy things. And a copy tensor then is just a tensor with sort of, say, 3 indices. And when any of those indices are the same, then this is u to 1. So the multiplication gate is a special version of this copy gate where you just have binary indices. Okay, so this is basically sufficient now to construct arithmetic. And I'll just show you some examples. So it's very, very straightforward. Okay, so imagine that I want to just consider this function, 2-dimensional function, which is the sum of 2 1-dimensional functions. It's just given by the tensor network, this tensor network, and the contraction of this object. The implicit thing that's going on is that when you just write down 2 tensors, then implicitly they are being multiplied, right? So if you take 2 tensors and just put them next to each other, implicitly there's a sense of multiplication. And this binary index here is being controlled by the addition to ensure that this f is in one case its values, and g is switched to the number 1, so f is times 1. And then in the other case, g is its values, and then f is switched to the value is to the number 1. And then tensor network contraction just sums over all the possibilities, and so you get this summation here. Similarly, now if I want to do this more kind of traditional summation where it's in the same variable, then I can just take the input and copy it, and then I have f of x plus g of x. And this is multiplication. So multiplication just ensures that both of these functions are switched to their values. So this index is set to 1. And then finally, this is squaring. So squaring, I have to copy the index and then multiply the thing together. Okay. And then, of course, integration means I have to sum over the inputs. So I can just sum over one of the indices. So this way, I can compose any function or any transformation of functions through an arithmetic circuit, and then I can integrate it by summing over the index. All right, so now I'm going to consider a specific application. So I'm going to integrate multivariable polynomials. And it turns out that this example is very rich in structure. And so we'll focus on it basically for the whole talk, except for one slide at the end where I discuss other things. So I'm going to integrate this class of polynomials. So this multivariable function is going to be a product of many polynomials, k of these polynomials. Each of these is a multivariable polynomial. And then each of these polynomials will have a special structure where it's just a sum of univariate polynomials. In fact, I'm going to relax this and say it's just a sum of univariate functions. But if you want to say it's an overall polynomial, you can think of each of these as univariate polynomials. So one can show that I'm going to integrate this on the unit cube, and one can show that for special types of polynomials, this integration is NP hard, because somehow you can map it to the SAT problem. And so this is in general not something you can easily do. But the basic idea is we're going to try and express this polynomial as an arithmetic circuit of tensors, then contract the tensor network, and therefore approximate this integral, and see if in practice it's easy or hard. Okay, so the circuit, okay, it has to multiply some things, and these things are sums of things. And the circuit just looks like this. Okay, so basically these are the values x coming in, they're copied, and the first copy they go into A, which is evaluated, and then it's added to the value of A2 and added to A3, and then it comes out as this on this index here. This is the value of this multivariable function, and this other copy is put in this row here and evaluates to B, and this other copy is put in this row, evaluates to C, and of course you can have many rows, so you can have you have order k rows. And then everything is multiplied together. Pretty simple circuit in that sense. Okay, so now when you look at this, it has a very regular structure. It looks like a grid, and if you want, you can actually map this to a kind of tensor network that one is very familiar with in quantum physics by just grouping some of these tensors together. So this is a very regular tensor network. Looks like this, and let's imagine just grouping the tensors and contracting them together like that. And so if you want, I mean, you don't have to, but if you want, you can say, let's group all these things together. And then it just looks like tensor networks contracted on a square grid or rectangular grid. And that's just a familiar tensor network in quantum physics known as a PEPS. And because one knows how to reason about PEPS, then this is a convenient, this particular description is convenient language to reason about things. Okay, so this is a projected entangled pair state defined on a rectangular grid, where the width is a number of variables and the depth is a kind of nonlinearity of the problem. Okay, it represents how many times a variable is copied before it's being manipulated on. It's not strictly the nonlinearity of the polynomial, because these univariate functions can be as nonlinear as you want, but it is a kind of nonlinearity. And it turns out this nonlinearity is very important in understanding the complexity. Okay, so we can now contract this tensor network, and this evaluates the integral. And one can contract this a variety of ways. And as I said, you could just contract it exactly. If you did it exactly, you would be performing the quadrature exactly. And worst case, exact contraction is exponentially hard, just like quadrature. But it's important to point out that it's not always exponentially hard in the variable, in the dimensions of the input. To see a simple case where it's not, consider the example where the number of variables is very large, but this nonlinearity, the number of layers, is very small. In this case, this type of tensor network can be contracted essentially just from the left to the right, with a cost that is just linear in the number of variables, not exponential. Okay? So in this setting, which is a very high dimensional setting, you would get an exponential speed up over exact quadrature while producing the exact result. Okay? Of course, the cost is hidden in the exponential dependence on the nonlinearity, but it just suggests that there's this certain set of integrands where you can do it very, very quickly. Okay, but I'm not really going to do exact contraction. I'm just mainly going to do approximate contraction. The idea here is that we have this tensor network. It looks like a standard tensor network, and so I know how to approximately contract it. If you do physics, you have these types of programs, and that's what we use. And we're basically going to contract these rows into each other and then compress the rows. So for example, these are two rows that are contracted together, and then compress them into single rows where the bond dimension has been reduced to some preset value m. Okay, so we're going to do this linear algebra to reduce these large dimensions into some low rank factorization of dimension m. And then we're going to control this rank and increase it and see how the error behaves as I increase the rank or the bond dimension. And that's the basic strategy. Okay, so let's start with a very simple example. Okay, so in this simple case, I'm going to consider this function, which I'm going to take as a product of these polynomials. And in general, the polynomials can be all different, but I'm going to consider a simple case where all the polynomials are, in fact, the same. Okay, so it's just the same multivariate polynomial raised to the kth power, and I'm going to integrate it on the unit cube. And remember that this univariate polynomial is this multivariable polynomial is just a sum of random univariate polynomials, the univariate function. Okay, so I'm going to integrate the hypercube and put some number of grid points down. I'm going to do it in 20 dimensions. The number of dimensions is not important because it turns out the cost does not depend on the dimension really, just linear in the dimension. And this is the result. Okay, so this is the error in the integration as a function of the compression dimension. Okay, so this is the approximation we're making. As it goes towards the right, you're treating larger and larger tensors, and you see, of course, the error is naturally going down. And the different colors here are the amount of nonlinearity in the problem. So k equals 5 means like the input's copied 5 times, and then I can't read what this says, but it's probably 10 or 15. This means the inputs are copied 4 times. Again, so the error is increasing as the nonlinearity of the problem increases. But there's a rather interesting thing here, which is that at some bond dimension, some small rank, much smaller than the rank needed that you think you need to do it exactly, much, much smaller, exponentially smaller, the error goes exactly to 0. Okay, so even though I'm compressing this to some very small problem, the error in fact becomes 0 at some point. And so you can ask, why is this happen? And it's independent of the number of dimensions. So this always happens for this case. So the interesting thing is, well, it means that you've discovered an exact identity. Okay, so an exact transformation of variables, which makes the integral very simple. Okay, so this may be. You may have known this, but I certainly didn't know this ahead of time. So this particular integral can be done by some recursive application of the binomial identity very efficiently. So this is the sum of some things to the kth power. And you can see if you just take the sum of 2 terms raised to the kth power, you can apply the binomial identity. And so then it just is a sum of k plus 1 terms, and you can do these univariate integrations. And then you just apply this formula recursively, and you can do this thing very efficiently. So basically, perhaps you already knew this, but the point is that during the compression, we just discovered this. And in fact, this is a way to you can generate new classes of identities in this way. So it's kind of an interesting trick. But of course, one's not always so fortunate that there is some sort of exact identity waiting to be discovered. And so the question then becomes, what happens in the more general case? Okay. So in the more general case, you have these different multivariate polynomials, A, B, and C. Okay. And I said, well, there's a special case when they're all the same, the symmetric case. It turns out to be very easy to integrate, very easy to contract. But now let's see if they're not the same, how easy is it? And how does the cost of doing this to get some certain error, how does it depend on various factors? So an critical factor, as I mentioned, is this sense of nonlinearity of the circuit. It looks like it should govern the cost. There's, of course, a number of dimensions. This is not actually going to be very important, although it's the original sort of curse of dimensionality is associated with this. And then finally, does it depend at all on the types of functions we put here, these univariate functions? For example, I can choose these univariate functions to all be positive, then the whole thing is a positive integral, for example. Then there's no sign problem in Monte Carlo. Or I could choose them to be very oscillatory, and that would change the nature of the problem for Monte Carlo. Okay, So let's just look at these three factors. So first, we look at the dependence on the nonlinearity. And I'm going to basically take the symmetric point where A, B, and C are the same, and then just perturb away from it. So I'm going to choose this second polynomial B to just be a little bit different from A, the third polynomial C to be a little bit different from A, and then see how it depends on moving away from the symmetric point. Okay, so this is for very small perturbation away from the symmetric point. And this is showing the error as a function of the nonlinearity. These are the different colors. And on the x-axis is the compression dimension. And there's essentially now two regimes of complexity. So you see there's a low accuracy easy regime up here where I can increase the number of layers, the nonlinearity, and to get a certain error, the bond dimension doesn't change. It changes very mildly, just like the symmetric case. And then below a certain error, however, if you want to do it to all the digits, then suddenly you get this very hard regime where you need to perhaps increase the bond dimension exponentially with the nonlinearity to get the precision. And this is the same thing if I go further away from the symmetric point. So again, you have sort of two regimes. So there's some easy regime, but it's now smaller. So if you're interested in 10 to the minus 4 accuracy, it's very easy, but it becomes harder to get more digits in this less symmetric case. Okay, so there's some kind of easy to hard transition with respect to precision, which we don't understand in a theoretical sense, but anyway, empirically we see it's there. Okay, how does all this depend on the number of variables? Well, the nice thing is it just doesn't. Okay, so I can look at this here as I change the number of variables, and the complexity, which is just shown by sort of how quickly this is going down with bond dimension. I change the scale because my students change the scale. But anyway, this is a logarithm. It's just a different useful way of thinking about it. They all look the same. So there's not really any cursive dimensionality here. The complexity is really hidden on the nonlinearity, not in the dimensionality. And then finally, let's look at the case where I change the kind of nature of the integrand. So I can make it sort of, so remember that these multivariable functions are chosen as sums of univariate functions, and I can choose to make these values, for example, all positive, or I can make them positive and negative. So I'm just going to set these to take random values on the grid within some interval from some lower bound to 1. And if I set this lower bound to 0, then all the values are positive. So the function is just a positive function everywhere. Okay, you expect to perhaps be able to do this by Monte Carlo integration. If I set this to -1, then all the functions are going to be very oscillatory. So the functions just take random values between -1 and 1 on the grid. The total integral will be very close to 0, even though you're integrating over many dimensions. And then Monte Carlo would have a terrible sign problem, perhaps even exponential in the number of dimensions. Okay, so let's see what happens. Okay, so let's take the case where the values are between -1 and 1. So this is a very, very oscillatory case. So in this very oscillatory case, then indeed it's quite hard to approximate. So if you take if you take any bond dimension, you basically don't get very good answers until you reach some bond dimension which corresponds to the exact contraction of the network. And this is quite easy to understand in the sense that if your total value of the integral is 0, then if you're even throwing away small things, okay, then you essentially make large error. Okay, so even if I'm compressing, it just makes very large relative error, and that's essentially what we're seeing. But unlike the Monte Carlo case, the effort you need to put in doesn't depend on the dimensionality problem. It really depends only on the nonlinearity of the problem. So though I'm not showing this on this plot here, you get the same plot if I increase the number of dimensions. So the sign problem sort of appears, but in a kind of different way and perhaps better way in this case. Then when I make the values, a little bit less oscillatory because they now in a slightly more positive range, then the problem starts to become compressible again. So I can, don't have to use a very large bond dimension to get some, 10 to the minus 4 error. And then if I make it all positive, then it becomes more compressible. So
recording stopped. Recording in progress.
Just to say that there's, as I said, this type of sign-like problem doesn't have any dependence on n, so that makes it very different from the Monte Carlo case, and it essentially just depends on the nonlinearity. Okay, so I think that's all I want to say about polynomials. This is just one slide on other things. So I defined a way to represent functions as an arithmetic circuit you don't have to represent polynomials. So I can do other types of functions. This is, for example, the integral of the Gaussian in many dimensions. You might all think you can integrate Gaussians, and that's true if you integrate them between minus infinity and zero, or infinity and zero, but this is integrating on the hypercube, so it's not very easy to do. And you can write down some type of circuit that represents it. This looks like that. And this just to show here that, again, this integral can indeed be approximated. And as I increase the number of variables I'm integrating over, the amount of effort I need to get some accuracy, let's say 10 to the minus 6 or 10 to the minus 8, has a very, very mild dependence on the dimension. I don't know theoretically what is, but it doesn't look like it's exponential. Okay, so just to summarize, this was I spoke quite quickly, so quick talk. So general multivariable functions can be represented by an arithmetic circuit defined the way that I presented, an arithmetic tensor network. This opens up the approximation of integration. And this type of way of doing high dimensional integration has very different characteristics, it seems, to the techniques that people use. So compared to quadrature, which always has this exponential to the n scaling, the dependence on the number of dimensions is very mild in the tensor network. It can be just linear, or in the Gaussian case, it's probably not linear, but something mild, maybe quadratic. And compared to Monte Carlo, where there's a sign problem, you in fact have a version of this sign problem, but it depends on different things. So it doesn't depend on the dimensionality very much, but perhaps it depends on nonlinearity. So that's what I wanted to say. This is still work in progress, and this work was powered by the QIM software package developed by Johnny, and thank you for your attention.